Hello everyone, my name is Prashant Lakera and this is a part 5th or the last part of the performance tuning from the scratch series where I am going to talk about the IO management or more specifically to disk IO subsystem. So this which is considered the slowest of among all the parts. So how can we tune that the various parameters? Uh, what are the different components which are involved? How actually application writes the data? What are the different elevators which is provided by the Red Linux starting from 2.6? All those things which we are going to discuss in this IO management. So before going into all those parameters and everything, let's see how a user application ultimately write the data to a disk, because like we see in the memory section, most of the application doesn't write their data directly to the disk, or in case you unless or until you are using a direct IO. So most of the application you are writing the data inside your cache, and then you have threads like PD flush or per BDI flush threads which are pushing the data back to the disk. So let's see how this data is ultimately writing to our disk. So like I mentioned, most of the data is inside your cache memory or your buffer memory where your inodes or directories entities reside. Okay, so let's say we have a user who requests to write a file through the simple write system call, which has been initiated by the glibc. So like we and as I mentioned, like we have a different kind of a threads like PD flush threads or per BDI flush thread, which need to return the data back to the disk. So between this scheduler layer and this VFS cache layer, we have something called a bio layer that put each block buffer together to a bio struct and submit a write request to the block device layer, which is our IO scheduler layer. In the IO scheduler layer or the this layer, all your merge operation take place. So means IO elevated layer and means means all your means merging, and means it depend upon the type of elevator you are going to use. It take place, and just put your request in a different IO queue. Device driver, then it ultimately moves to your device driver, which is majorly a SCSI or other device specific driver, which is generally taken of the write operation. And last but not the least, we have something called a firmware, which performs your hardware operation like seek head rotation, rotation and data transfer to sectors on the platter. So this is how the entire process works. So the main thing we need to remember that, like whenever your data means it's not like you have a single disk between your cache and the disk. There are lots of layer, like a scheduler layer, we have a device driver layer, and ultimately the data return to your disk. Or nowadays we have a sense storage where the data ultimately return to your sense storage. So let's look at the cache memory, which is an important part of your memory. So if you see the output of your free-m, you see this cache memory, this, and this is your buffer memory. So cache is one of the major component, but it is the first place where kernel looks at when it is looking for the free memory. So whenever you are looking at the free memory component, you never need to look at this component, you need to look at this component, which is a combination of free plus buffer plus your cache memory. Okay, so let's go back to the presentation. Your cache memory. Okay, so if we look back in the last like 5 or 10 years, the performance improvement has the speed of our yes, CPU has, or our processor has increased in a considerable amount as compared to other component like your cache or a disk or a RAM, and disk is always a several magnitudes slow as compared to your CPU registers. So means slower access to memory and disk restrict overall system performance. So system performance is not enhanced by your whatever the speed improvement which will help on the processor side. So cache mechanism generally helps us to resolve this kind of a issue, where the data is not directly being pushed to the disk, it is being pushed to the cache, which is comparatively much faster as compared to your disk. And it will depend upon your, we are talking about your RAM, means they're like all like nowadays we have a CPU who have a L1, L2 and L3 cache, and means, and also we have a something called TLB or transition data set buffer. So if you look at this, like earlier we have like a CPU and a disk, just refer to this architecture. in the first figure. So CPU which is register which are really fast, and disk which is really slow. So there is a greater mismatch in the terms of speed between the CPU and a disk. While in second case we have CPU register which is obviously very fast, then we have a cache which is comparatively faster, then RAM which is slow, and disk which is ultimately really slow. So what we are doing, we are directly reducing the chances of having access to a slower memory. Currently, like all of the IO component which we are dealing with nowadays, for example hard disk or a disk controller or a file system, has its own caching mechanism to handle these kind of stuff. So means all the application, like your hard disk itself has some sort of a cache, the disk controller itself has some kind of a cache, while the file system has own cache mechanism. So means everything will having some kind of a technique to handle this cache. And so whatever the aim of each and everything is like to achieve the higher cache hit, which is going to improve your performance up to a large extent. So for this we have two stuff called locality of reference, which is divided into two categories called temporary locality or spatial locality of reference. So in temporal locality means the data most recently used has probability of being used in near future, and that is why your kernel try to cache that data so that it don't need to go to the slower medium, that is this, which is several magnitudes slow as compared to your CPU register. So always like most of our data which is being accessed one time, generally it is been put in the cache, so that in case in future if that data need to be need by the application, the kernel or your CPU doesn't need to go all the way to the disk to fetch the data. The second one is called spatial locality of reference, which means that the data that is reside close to a data which has been used has a high probability of being used again. And for that purpose, we have used a parameter called read ahead underscore kb. So we are going to discuss these later. So means for both of these, the temporal locality or spatial locality, Linux uses concept for your page cache, your file object cache, which we have already discussed, like your inode cache or directory entry cache, and read ahead buffer, which we have just discussed. So for all these things, Linux uses the concept of both temporal locality as well as spatial locality. Okay, now let's discuss a little bit about this elevator. Like I told you, like whenever the data goes from your bio layer to the IO scheduler layer, so means bio layer or a block layer or bio layer act as the interface between your file system layer and block layer. So at the IO elevator layer, we have like a lot of thing going on, like for your merging of a request to the means most of your merging requests will take place, like shuffling of all these requests will take place. So before 2.6 kernel, the 2.4 use a single general purpose IO elevator, but starting from 2.6 we have a 4 choices of elevator. And if you look at the rel kernel, like rel 7, you only have a 3 scheduler available. So if you want to check like what scheduler which is currently been enabled in your system, you just need to go sys block sta whatever the disk you are using, q, and scheduler. So here we can see that the default scheduler we are using is the CFQ scheduler. If you want to change the scheduler to some other scheduler, you can change it with the help of this command. So now you can see that deadline become a default scheduler. Yes. So now look at this scheduler option one by one. I'm not going to discuss it because it is not using anymore. So first discuss about the noob or no operation. As the name suggests, it's like a no operation. It is just a simple line of a code or a simple FIFO, that is first in first out queue, where it is not going to do any sort of a data reordering and data ordering, which is generally been happen on other scheduler. So it's do some sort of a merging but no data ordering. So it's generally have a very low processor overhead to disk IO. So it's generally been used, like for example in case of your virtual machine or in a storage who has its own elevator mechanism. So no operation is used in case of in these kind of examples. deadline. This is one of the most misleading scheduler which is being used by a database. So as the name suggests, deadline, that it is need to meet some kind of a deadline, but actually it does not dispatch every IO before deadline. But the way it does, or way it treats those, that it give additional consideration for IO who has passed their expiration time. So in this way it works. It's generally been used for your database purpose. It always prioritizes read request over the write, and it ensures that the starvation doesn't occur for resources. So generally it is been suitable for your database. Now CFQ is the default scheduler. I think 2.6.18 is become the default scheduler. It maintain a per process IO queue. So generally, in case of your desktop environment, where you have a large multi-user environment with lots of competing processes, or where you are not sure about the load average, generally CFQ is the default scheduler, or the scheduler which has been recommended. Okay, uh, you can manage these scheduling priorities with the help of ionize command, and like the name says, CFQ, it will attempt to draw fairly from all queues, like it maintain a per process queue when collect pending requests for the request queue. Okay, so if you have a separate hard disk, for example, you have a separate hard disk log, let's say sysblock sdb q sdb. So for that, what you can do, you can choose a different scheduler. For example, for sd I want a deadline, but for sdb I want to choose a noob. So uh, you can do that. So because this system has only one hard disk, you I can even do that. That for SDB I can choose no operation as a scheduler. If you want to set out a default value for all the scheduler, or for all your hard disk, you just need to do one thing. Just go to your bootgrub.conf, comes to your kernel line, and here you just need to append one line: elevator is equal to no, or whatever the elevator you want to set it out. And this way it will be read on the at the boot up, and it will set out that value for all your disk, whatever the disk which you are running in your system. So here I'm just using a virtual machine with just a single disk SDA partition. So for me, like I mentioned, I set up this scheduler. Okay, okay, so locality of reference, IO architecture, cache memory, and I already show you how to change the scheduler. Now there are some tools which you can use to debug this IO bottleneck. So most popular you have like vmstat. When you run with this option, by default option, you can see like how many blocks are in and how many blocks are out here, because this system is not doing anything much, so you cannot see anything going on. But let's generate some IOs. Root, no, and okay, why the system itself needs some performance tuning. Okay, input file, output file equal to dev0, and let me put this process in the background. Okay. Now check your no block in, no block out. Awesome. Okay, begin dd input equal to /f0, output equal to mnt testing, block size is equal to 1m, count is equal to, let's say I'm generating this much big file. Okay, now check vmstat. So you will see that the number of blocks which are going on here. Okay, let's kill this process before it fill up my system. Okay, and let's remove this file to mnt. Okay, one more tool I want to show you is SAR. So with SAR, using -u option, you can check something called IO weight, in which you can see that there's some kind of performance issue. Okay, and like VMstat, you can check like number of blocks in and number of blocks out. Same way you can check if there's some IO weight is going on. Okay, one of the biggest problem with these kind of a tools, like you will see like, okay, if you see like 80 or 90% of IO weight is going on, like something is going on in your system, but you never know which process is responsible for creating those IO weight. So starting from 5.8, we have a tool which is similar to, like, we have a top, which is going to give us a like a interface, like real-time interface of like which process is consuming the most CPU or memory. Similar way for IO, we have tool called iotop, which is going to tell me like which process is doing like a disk read or write, all these things. So here I can figure it out, like which process is doing what. Okay, so iotop is a really handy tool to debug any performance issue where we want to know like which application is doing the read or write for us. Okay, and now the most used tool called iostat. So iostat 1.3. So if you run iostat without any other option, it doesn't give you much useful information like transaction plug per second, block read, block write, uh, write per second, or block read or block write. But if you run with tkx-p 123, oh, you get a hell lot of information. And this is where the real power of iostat comes. So, but before going into depth of iostat, I want to show you one thing. Just remember this diagram, because the iostat main page is somehow misleading. So if you go to menus of iostat, for most of the places it used disk. Okay, so like I have something called RRQM. Okay, before going to a disk, just remember this thing, means it uses the system device as a whole. So what exactly this device? Actually this device is a combination of three things. So like I told you, this device actually means this scheduler layer, this device layer, and disk layer. Okay, scheduler, device driver, and disk. So whenever I talks about that, this RRQM first parameter and WRQM, so read request merge per second and the write request merge per second, the number of requests merge per second that were queued to the IO scheduler layer, not to the disk. Okay, so RRQM, so it says the number of read requests merge per second that were queued to the device. Device means, here it means I would not say the man page is misleading, but I would say it's interpretation. So read request merging take place at the scheduler layer, not at the disk. So whenever it say read request merge per second, that means that were queued to the IO scheduler layer here, where all the merging take place or where all the reordering take place. Same way for the write request, not device, but device the combination of these three things. Second thing is read per second or write per second. This one, read or write. So this is the number of requests that were completed by storage per second, number of requests that are completed by storage per second. This is very straightforward. Then read KB per second or write KB second is the number of kilobytes transferred between the host and storage per second. Reuse start from application side to the ultimately your storage, the number of data which is being transferred between both of them. This average request size, which is generally been calculated in 512 bytes sector of the requests that were completed by means request queue size, average request size. What is the request size, which is really important, which is in bytes, and it's 512 bytes sector, and it's the combined average for your both for your read request as well as write request. So the simple formula which has been used to calculate this is uh, read kilobyte per second plus write kilobyte per second, okay, multiply by 2 divided by read per second plus write per second, read per second plus write per second. This is the way your average request size is calculated. Okay, uh, I'm going to discuss about one of the scenario in which how you're going to deal with all these parameters. This is a pretty nasty one, the average queue size. So the average number of requests within your scheduler queue plus the average number of IO outstanding to storage. Okay, so this is where your most of your performance issue you will see. So this is like a number of requests within the IO scheduler queue here, and number of requests which has been on the outstanding to a storage here, which is called LUN queue. Okay, so means generally you will see the issue when, for example, uh, means most of the issues occur when means when the your average request size remains below your LUN queue depth, IO is passed quickly from all these combination. But when this number of requests increases, okay, then you will see the issue, and there is all when you see the performance hit. So as long as this average queue size uh, remain below your LUN queue depth, that is the uh, request which has been held by the disk, as long as this is remain below, your scheduler just pass the request to the device driver combo and ultimately to your disk. Device driver is one of the component which is not going to hold any of your requests. It's just going to repacking that request and send it to the disk. But whenever this your LUN queue depth filled up, and it is means whenever your LUN queue depth filled up, then you see all sort of performance issue. So always remember that your average queue size always need to be remains below the LUN queue depth. If it's become more than your LUN queue depth, then you see all kind of a performance hit. Okay, then the next component, which is called average wait time. So that it is a time which is spent by your request, time spent by request in your scheduler queue, and the time storage spent in servicing those requests. So the difference between this and the service time, which is like similar, looks similar, that service time will consider the parallel operation, while the average wait time don't take into account the parallel operation. Okay, like I told, service time means effective storage time for IO requests that were completed by the storage. So average wait is the time spent by requests in the scheduler queue and time storage spent in servicing those requests, while service time is just the effective storage time for IO requests that were completed by the storage, and is generally been measured in front of your scheduler and IO done time. Okay, and this is one of the component which has been seen by many of the system administrator called percentage util. So it's a percentage of sample interval during which there was at least one IO standing, at least one outstanding IO request within your IO scheduler driver storage combination. So means whenever you see that percentage utilization shoots up, then you see all kind of a performance hit. Okay, and in the whole of this I talk about some of this NR request queue, and like I told you about the request managed at the scheduler level as well as request which is being managed at your LUN queue depth. So what are those? So you can see all those things here. Sys block your device name, queue, and NR underscore request. which is 128. Okay, so it is just a way to increase or decrease that can be issued to the disk subsystem. So means it will entirely depend upon you. There is no best setting. You need to play with this parameter. Like if your storage is capable, it means it depend upon your, like I mentioned, the reason you see also kind of performance issue when your average request queue size remain means become greater than that of your learn queue depth. And the way you can see your learn queue depth is by sys block sda device and queue depth. So as long as this value nr request lower than this, your means request is just passed elevator from your elevator to device driver to disk. There is no issue. But when this grows up, then you see all kind of performance issue. This is just a default value which is in setup. So I will show you with the help of one example where you will see all kind of performance issue. Okay, the some tuning parameter is one is the nr underscore request. There is something called read ahead kb. So in case of a large streaming reads, how large read ahead operations in kb? So you can check this with the help of something cat sys block device, sys block your device name, your queue, and read ahead kb. Okay, and by default your whenever you mount, there is one last thing is called a time or no a time. So means Linux file system keep track of when files are created, updated, and access. So in case if you don't want like the update time, the means the files and directory update time is not important for you, you can use an option called no a time. So mounting it with no a time will prevent your inode access time for being updated. So means it's a very small performance improvement you will see after this, but means like you will see some sort of a performance improvement. So the one thing I want to show you, like here if you can see here the average queue size, okay, increases above the learn queue depth which has been set to 31. So here you see the percentage utilization shoot up to 100%. So as long as this value of average queue size will remain below your learn queue depth, you will not see any performance issue. And this might not technically a performance issue from the kernel side. This means your storage, you can increase that value, means you can play with those parameters and increase or decrease the size of your nr request, increase or decrease the size of your learn queue depth. But if you, even if you do not see any performance improvement after doing that, that means your storage is not smart enough to service your requests. So in that case you will need to request for smart storage, or you will need to means check your load. Okay, so this is just a brief introduction to IO subsystem, how the application write data to your disk, some performance improvement tips, some IO elevators, all these things. So thanks for watching this video. In case of any question, you can write it to me to at laprashant@gmail.com. Thanks once again.